Professor Peliti, over to you.
Hi. So today we're going to discuss about thermodynamic uncertainty relations and some related relations on first passage time. So the motivation for this is the fact that the fluctuation relations that we discussed, I discussed in the past lectures, are static in the sense that the time dependence does not enter explicitly in the relation. But in fact, from this point of view, they are similar to the thermodynamic relations, what you have in the classical thermodynamics. When you evaluate, for instance, the total dissipation related to a transformation of a system, that formally the relations you get do not depend explicitly depend on the time needed to perform the transformation. On the other hand, even for classical thermodynamics, there have been some results in which the time dependence is at least more explicitly considered. One of the classic results is due to Corazon and Alborn in 1975, that tells you what is the efficiency at maximum power. So you imagine that you have a machine that is works, but you want to maximize the power, and then you find that there is a relation, say Carnot-like a relation between the efficiency at maximum power and the ratio of the temperatures. So this is similar to the Carnot relation, but you see that you have the square root of the ratio of the cold temperature with respect to the warm temperature. And so in this case, we have implicitly time dependence because maximum power requires that you fit somehow the regime of work of the machine working. You have to fit the speed of the machine working in order to reach this condition of maximum power. So what we are going to do now is to try and find a number of results of a similar kind for stochastic thermodynamics. We can go at the essence is in fact that can be obtained by looking at the toy model of a molecular motor. So this toy model is simply an asymmetric random walk. You have a molecule that is on a one-dimensional manifold, say on rails on one dimension, and we denote by n. It's an integer n. It's in position at any time, and the different positions that the molecule can have on this rail are separated by a distance d, so that the actual distance from the origin of when the molecule is at in location n is equal to x times nd. And then we have that the molecule can step either on the right or on the left with some transition rates, k plus or minus, plus for going to the right, minus going to the left. And these steps are are facilitated by, for instance, ATP hydrolysis. But in the model we are considering, we suppose that these steps are tightly bound to ATP hydrolysis. That means that if it goes to the right, there will be hydrolysis of one molecule. If it goes to the left, then it will joins ATP with P and reproduce from ADP plus P, one molecule of ATP. So you have a chemical ATP imbalance delta mu that we assumed to be tunable, and there is an applied force. So there is, if the molecule moves one step to the right, there will be a work performed against the force. So this is it will be equal. This work will be equal to the applied force F times the displacement d. And because of thermodynamics, so we have these two sources of thermodynamical imbalance that allows us, by the generalized detailed balance condition, to write the expression of the ratio of the rate for going to the right and the rate of going to the left. And this is given, so this ratio is equal to the exponential of delta mu, which is the chemical ATP imbalance for a single molecule, and then minus FD, which is in this case, so the work that is performed by the molecule itself against the applied force, divided by KT. So this quantity here, a delta mu minus FD divided by T, I call A. It's some sort, is a measure of the imbalance, thermodynamic imbalance of the system. Now, with this simple model, we can easily look at what happens. So first of all, of course, we would like to evaluate the evolution of the probability for the system to have done a certain number of steps in the right direction and a certain number of steps in the left direction, starting from t equals 0 up to time t. So this is this probability, and this is very easy to evaluate by kind of master equations. So in master equation, we have that the derivative of this quantity is will be given by two inflow terms and one outflow term. So the inflow term, here we see that there is a probability, the probability that the number of steps to the right was 1 minus the n plus, times, of course, the rate of making one step to the right. Analogously, we can imagine that we have a situation in which the probability of making one step, so you start with the probability that the number of steps to the left was 1 less than n minus, and then you have the rate of doing one step to the left. And you have the outflow term, that is a probability, simply probability that n plus and n minus have given values and doing a step either on the left or on the right. This equation is trivial to solve because in this case, the plus or minus steps are independent Poisson processes. Therefore, the probability at time t of having done n plus step to the right and minus step to the left is given by usual expression of the Poisson probability. So the average value of the number of steps to the right is given by k plus times t, and therefore this probability will be k plus t times n plus divided n plus factorial times e to the minus k plus t. Analogously, you have it for the minus sign. Sorry, just a moment. Oh, you have analogously for the minus sign here. And therefore, we can use this expression to evaluate, for instance, the total number of the total average displacement in terms of the locations that is given by the difference between n plus and n minus. And will be given, well, obviously, by difference of the rates times t. And this quantity we write as J times t. So J is the current measured in terms of the locations. And we can also evaluate the variance of the number of steps. And this is given by this, because of the properties of the Poisson process, is given by the sum of the average number of steps to the right and the steps to the left. Therefore, it's given by the sum of the rates or jump rates, and we write this as twice like diffusion constant times t. This is always in units of this n. Now, by the Schnackenberg relation that we have seen yesterday, we can write down the mean rate of entropy production. And the mean rate of entropy production will be given by the Boltzmann constant times the difference of the rates, say going to the right minus going to the left, times the log of the ratio of the two rates. Now, the log of the ratio of the two rates, because of the relation that we have here, is given by A. So there is A over KB, and this quantity here is J that we have defined here. So what we have is that the mean rate of entropy production is given by the product of this current J times this imbalance A. Now, let's look. We have this expression of the probability distribution of the number of steps, and we can look at it, what happens for large values of the observation time t. Now, in this case, what we have is that this probability satisfies a large deviation principles. That means that we can express this probability in terms of quantity that it decreases exponentially with the observation time, and depends on the ratio of the, depends on the number of steps, average of the number of steps that have been performed per unit time. So the idea is that for you are looking at the system after a very long time, and you evaluate the ratio of the number of steps to the right divided by t, or the number of steps to the left divided by t, and this defines this quantity nu. Now, you can express this probability of having done these steps and to the right, to the left, in terms of this quantity nu, and you find that this can be expressed asymptotically up to, say, less, up to smaller factors, as exponential minus t times some function that is a function only of this ratio. So that the main dependence on time is this common factor t. Now, this function omega is called the larger deviation function, and in this case is very easy to evaluate, and is given by this expression, in which we see that appears the ratio of the I would say velocity, say empirical velocity, because it just fluctuates depending on what is the trajectory you're looking at. So it is the ratio of the empirical velocity with respect to the jump rate. This is for the positive jumps, this is for the negative jumps, and here you have some terms that are needed essentially for normalization purposes. Now, so this tells you that in some sense that the correct way of looking at what happens in this situation in which the system settles on a steady state, but you want to know what happens in trajectory by trajectory, and therefore characterize the dispersion around the average behavior, is by looking at this larger deviation function. But in our case, the things are even simpler, because we have that on the one hand, that the average displacement grows linearly with time, and also the uncertainty in the number of steps grows linearly. So the dispersion, so the deviation, this variance of the number of steps and the average number, net number of steps, they are both proportional to t, and in order to remove the dependence of c, we just take the ratio, This ratio is called the Fano factor for this process. And by using the definitions that we have seen before, what we get is that this is equal to 2d divided by j, and can be expressed in terms of the jump rates in this way. And since and by dividing, say, by k minus, you can express this quantity, this ratio of the jump rates in terms of the hyperbolic cotangent of this affinity A divided by 2kb. Therefore, because the hyperbolic cotangent is always larger than or equal to 1 for positive quantities, what we have is that the Fano factor must be larger than this argument of this. The cotangent is larger than or equal to the inverse of its argument. So what we have is that the Fano factor must be larger than or equal to this quantity 2kb divided by A. And this is interesting because this Fano factor for the displacement of a molecule on its substrate is directly observable. And therefore, if we can measure this Fano factor over a certain number of experiments, we are able to infer what is this affinity imbalance that appears here, and which is in fact responsible for the biasing the random walk. There is another quantity that we can evaluate, that is the relative uncertainty. The relative uncertainty is given by the difference of by the ratio of the variance with respect to the average of the net number of steps. And by using what we have written, what we get is that this quantity is equal to 2d divided by j squared t. So this relative uncertainty decreases with time. That is a consequence, if you like, of the central limit theorem. On the other hand, we know that the total entropy produced will be given by the average entropy production rate times the elapsed time. And therefore, the product of the total entropy produced times the relative uncertainty does not depend on time. And it can be expressed in this way in terms of the entropy production, the diffusion constant, and the average current or the average speed of the molecule. And now we know that the entropy production is equal to the current times the affinity A. So this can be simplified, and again, what we end up with a expression that involves the ratio of 2d divided by j, but at this time it's multiplied by a, and so we have that this quantity is equal to a times a hyperbolic tangent of a divided by kb, and again, by using the inequality for the hyperbolic tangent, this quantity is larger than or equal to twice the Boltzmann constant. So this is very nice because it's clean, and so it sort of bounds something that is related to the relative uncertainty and the entropy production, and in a universal way. On the other hand, we have that the entropy production itself is harder to observe because that is, again, depends on the value of the imbalance of the affinity A. Now, anyway, when are these inequalities saturated? Well, one trivial case is when you have very close to equilibrium. In this case, A is very small, and you're looking at, let's say, the value of a hyperbolic tangent for very small values of its argument, and you can find that, in fact, this becomes a 1 over the 1 over the argument, and then so you get that the inequality is saturated. But there is another situation in which A goes to 0, and if we look back here, we find that if the work done per one step is exactly equal to the difference in, to the chemical potential imbalance, then essentially we are applying to the system a force that is so strong that basically the motor is not able to move against the force. It will keep fluctuating around the original position, perform some unbiased random walk, in fact. And in this case, A goes to 0 again, and we can use the same argument to say that the inequality is saturated. Now, this has been done in a comparatively simple model, but we would like to have something that is more general. But but it is interesting to see that, in fact, you can say infer. You can infer from this relation the efficiency of the engine just by. And here what we have is that, for instance, here in this case we have a measure. The dots are measurements of this quantity 2d divided by the velocity times the displacement. That is related in our case to, so it's proportional to what we call here n. And here we have a concentration of ATP, which is a measure of how far we are from equilibrium. Say it's a measure of the imbalance of ATP. These data were taken by Fisher et al. About 20 years ago. And there is, by using these results on the imbalance, you can evaluate the efficiency, and you find that there are regimes in which, so the bounds, say the bound can be translated into a bound for the efficiency. And here there are the levels of efficiency that you can expect, and you see that the operating region of this kinesin motor goes from a region in which the efficiency can be even larger than 80% to something about 60%. And again, the same thing can be written now in terms of the same quantity, that corresponds essentially to the Fano factor, if you like. It's basically the Fano factor, and the applied force. These are the experimental results, and these are again the curves that constant efficiency curves for this kind of system. Now, we would like to have a more general argument for relations of this kind. And we start, in order to have this argument, we start from fluctuation relation, say detailed fluctuation relations for the total entropy production given the empirical current. Now, the empirical current is, so here is essentially the net number of steps that the system is doing, but in the proof that we are going to make, we are not supposing that there is a tight binding. That is, that there can be fluctuations in the number. Put it another way, the molecule can perform steps without consuming ATP. And of course, the dynamic is different, but this relation holds in general. that is a probability that the total entropy production during a finite interval of time and has a certain value, and the net current, that is the net number of steps, for instance, during the same interval, has a given value, J, this is equal to the probability that the total entropy production has the opposite value, and the number of steps, net number of steps, has also the opposite value, times exponential of the total energy production divided by kb. And this can be done by using the Crookes relation in this way. So we express the total entropy production with the probability, joint probability of total entropy production and the current by integrating over all trajectories. So we are in a steady state in the sense, so there is no manipulation, there is just imbalance. So we are integrating over all trajectories with the probability of the trajectory, and then we insert the constraints that the total entropy production is given to some value, and the net current is equal to some value. Now, by using the Crookes relation, the probability of the trajectory x is related to the probability of the inverse trajectory of the reverse trajectory by exponential is equal. So the probability of trajectory x is equal to exponential of the total entropy production divided by kb times the probability of the reverse trajectory. This is what we have seen, I think, in the day before yesterday as a Crookes relation for the probability of a trajectory. Now we can pull this factor out, and we change our integration variable. We change our integration value from x to the reverse, that x, and therefore, if in doing this, the sign of the entropy production changes and the sign of the current changes. So we obtained this expression. Here there is a hat missing. So this is integral over the reverse trajectories. And of course, this can be interpreted of the probability with the opposite value of the entropy production and of the current. Once we have obtained this relation, we can introduce a probability distribution that is restricted to positive values of the entropy production. In this way, we simply sum the probability of having, say, the given value, positive value of a total entropy production, and the probability of having the opposite value of the entropy production. And of course, what we have is that this total probability of having the value, say, given value positive, a given value, and the opposite of this given positive given value is given by the probability of having the given value, given positive value of the entropy production and the current J, times 1 plus the exponential factor that we have seen before. It is easy to see that this positive probability, let's call it, is normalized. So, of course, it is normalized over the positive values of the entropy production. And therefore, we can evaluate what is the average of the current over this distribution. So this is the average of the current, in principle, is just the given by the integral over all values of the entropy production, all values of the current itself, times the joint probability of current and entropy production. But now we restrict to the positive values of entropy productions, and we use this expression. Oh, I got a sign. I got the wrong sign here. Yeah, there was a wrong sign here, and it goes this way. So what we get is that going from this to this, we have that the probability of S dot is equal to the probability P plus times 1 minus S dot KB. And therefore, what we get is that the current itself is given by the integral only on the. So here, what we are doing is that we are summing the positive part and the negative part with the values of J. And because J changes sign when the entropy production changes sign, we have this minus sign here. So this is using the relation and taking into account the fact that J changes sign. We now use this second relation, tells us that P is equal to P plus divided by this factor here. And so what we end up is that the average value of the current is given by the integral over this P plus distribution of J times this correction factor, which you can see it's essentially a tangent, hyperbolic tangent. And therefore, this total average of H is given by the average of J times tangent of the total entropy production evaluated with P plus. On the other hand, the total entropy production is also given by so for the same reason, essentially, if instead of J, we put here S dot empirical, S dot, sorry, we get that the average total average entropy production is given by the average over only the positive values of the entropy production of S total S dot times the tangent divided by 2 KB. So this is actually within the thermodynamic uncertainty relations, probably the simplest one that I have found. And it tells you that it's sort of, it's a bit acrobatic. Now, in order to have the inequality, we use the Cauchy-Schwarz inequality. It tells us that, so here what we have is essentially a correlation. It's a correlation between J and the tangent, hyperbolic tangent of S dot divided by 2 KB. And the Cauchy-Schwarz inequality tells us that the correlations must be smaller, say, in some senses, must be smaller than the product of the average, of the absolute value of the averages. And so this is, sorry, absolute value, the product of the variances of the errors. So here what we have is that the square of this correlation between J and the tan, hyperbolic tangent, must be smaller than the average square of the current times the average square of the hyperbolic tangent. So this is just by Cauchy-Schwarz inequality. But then here we have the hyperbolic tangent square. And now the argument is always positive. Therefore, for a positive argument, we have a tangent square is always smaller than tangent, hyperbolic tangent of the, so, and therefore you have the average, and by using also the fact that it is a convex, for X positive, the hyperbolic tangent is convex, you can use a Jensen inequality, and eventually what you end up is that this average value must be large, it must be smaller than or equal to the hyperbolic tangent of the average of the argument. Therefore, what we get out of this is that the average value of the, say, the variance of the current must be larger than the average value of the current times 1 over the tangent of, so because you put this downstairs, so minus the average value of the tangent minus 1, and this can be recast in this form. So we have that there is a connection between the variance, the average value of the current square, and this connection is given by this expression in which the total entropy production enters. Now, in a steady state, the total entropy production is proportional to the duration of the process, and the variance is also proportional to the duration of the process. So we can write down the average value of J as average current times T, average entropy production as entropy production rate times T, and also we can say define this variance of the current as some constant quantity times T. You plug this in and take a limit to small t, and you find this relation, which is a quite general relation of the uncertainty relation. It's called uncertainty relations because in some sense, so this is the uncertainty on the value of the average current. This is the value of the current in the state on the current in the steady state, intensive current on steady state, and this is and so this it tells us that the uncertainty on the current cannot be smaller than a certain quantity, which is bounded by the entropy production. In other words, you can read out of this relation the fact that if you want to be precise, if you want the speed of your engine to be fluctuating little, you have to have a comparatively large entropy production. So the entropy production is here on the denominator. And if you want to reduce this value sigma square, you have to increase sigma dot. We can generalize this relation to the case in which you have multiple currents. Now, and in fact, it is quite easy because you can imagine that if you have multiple currents defined on the same trajectory, for instance, in the case of an engine, of a molecular motor, you can consider one current is the displacement and the other one is ATP consumption. But you can imagine a situation in which you have more currents, and in fact, because you have more, reaction loops within the system. Say that you have currents at J alpha, each defined on a trajectory X. And so you can, out of that, you can arbitrarily, define a linear combination of these currents and have a generic current J for which the previous inequality holds. So define this, this is the linear combination of the currents we're interested in. And then there is this quantity K that is defined in this way in terms of the average value of the entropy production. And then out of the relation that we had here, we have that, so out of the relation that we had here, this relation here, where the variance of the current appears, we can write down this inequality. Now, in this inequality, what we have is that, so this first term is the variance of this linear combination, but we are just split it into contributions given by the correlation matrix of the different currents at J alpha. So you are simply expressing the variance of the current J in terms of the individual correlations of the currents. And on the other hand, here we had the total value of the, we had the J square, values of J square. And again, this one can be expressed in terms of the linear combination. You pull out you get the product of the two average currents, and you times the coefficients on the linear combination. You pull them out, and you find that this expression must be positive. But now these lambdas are arbitrary, so you can choose this lambda by, say, you choose lambda to be equal to this expression, in which you have the average value of, say, gamma of one of the currents times the inverse element, so the element alpha gamma of this inverse of this correlation matrix. You know, the correlation matrix is positive definite, so you can always do that. And then you sum over gamma, and for each and you obtain the value of lambda alpha. You take this expression, you plug it in, and lo and behold, what you get is this inequality. In this inequality, you see here, there is average value of J, average value of J alpha, average value of J beta, times the inverse element, so this element of the inverse correlation matrix. And here we have the same quantity to the square divided by 1 over k, where k is this expression. Of course, you can divide this by this factor, and you end up with the general thermodynamic uncertainty relations in this form. So here we have the average values of the currents. Here we have the inverse elements of the inverse correlation matrix, and the sum of this quantity over all the currents must be smaller than or equal to this k factor that we have seen. And again, we can now look at what happens on the intensive quantity by introducing the duration or duration t of the time interval in which we are looking at the system, and this can be expressed in this way. So we have that the sum over alpha and beta of the average values of the currents, so intensive value of the current, so this must be okay, and times the element of the inverse of the correlation between the currents, between the intensive currents, must be smaller than or equal to the entropy production divided by 2kb. And again, what we have is that if these j's are kept constant and you want to reduce the average, you want to reduce the uncertainty, so that means that you are trying to reduce at least the diagonal parts of this correlation function, then you have to increase the rate of entropy production. Let's see how this works in an explicit case. So this is a kinesin model. So a kinesin model, you have 2 degrees of freedom. 1 degree of freedom is the location of the molecule on its substrate, and here we have this location A, B, and B, etc. And then there is the other degree of freedom is the amount of ATP molecules that have been dissipated in the world. And what we have is that the process goes in this way. If the molecule sits in this position A, then it can either go to B, say to this position B on the right or on the left by random motion without expending ATP, or it can go, say, it can charge, it can go up in this way by using a molecule so it goes from a site of A to a site B, but using one molecule of ATP, and then it can again either go back, release the ATP and go back to the same state, or at this time just by random motion go to this following A, and it can always go also in the reverse direction. So we have two possible kinds of state, say bound to ATP, bound to ADP, or empty. And the possible motions are either Brownian motion, you go from, so you are in state 1, or you are in state 2, which is bound to ADP or empty, and you can go in Brownian motion either to the left or to the right with some rate. You can bind to ATP, that is from state 2, you go to state 1 with some rate. You can go, say, one possibility is that you expand one molecule of ATP to move to the right, and this is called a ratchet move. There is a reverse ratchet. You spend your ATP, but you move to the left with some rate. And finally, you simply dissipate your ATP without moving. And that is, you go from state 1 to state 2 without changing your location. So all these rates can be expressed in terms of the applied force and the chemical potential imbalance of ATP. And some of them are even measurable, and some you can conjecture and adjust them by looking at the behavior. So what we have here, for instance, are data again by Fisher that we have seen before, but in a different garb. Here we have on the x-axis there is a concentration of ATP in micromolar units, and on the y-axis we have the speed of the machine. Yes?
Can I ask a question?
Yes, please.
Yeah, in the previous slide.
In the previous slide, yeah.
Just to understand clearly, so here you are considering a model of a molecular motor which can bind to a microtubule and see a ratchet potential and move, and
right.
It is doing a Brownian motion, right?
Right.
Okay, and okay, so then the omega plus are greater than omega minus, so it has a bias.
Yeah, I say, of course, you would like omega plus to be larger than omega minus, because and probably will be much larger. But in principle, all reactions must be reversible. Otherwise, we are in trouble with the thermodynamical consistency. You remember the thermodynamical consistency tells you that for each transition, transition for which the jump rate is positive, the opposite transition must also be positive, must also have a positive rate.
Okay.
So this is why we have to introduce also these possibilities of doing the reverse ratchet.
Right. And can I ask you a related question? Maybe not, I don't know if it is relevant at this point, but suppose if I had an experimental trajectory of such a motor which is doing this kind of a stochastic trajectory. So, and if I know experimentally these rates, do you think we can back calculate from the trajectory knowing the rates, this stochastic thermodynamics?
Okay, so the point is, can we infer the rates out of the trajectory? Well, in principle, yes. The problem is that the internal state is usually not quite easily measurable. And there might be also some internal degrees of freedom that are not directly measurable.
No, so I was saying that these rates can be experimentally measured, right? Separately.
Well, let's put it this way: with the data of Fisher, these authors were not able to some of the rates were measurable. I don't remember which ones, but then they had to introduce some sort of fudging factors to take into account the effects of the, say, the formation of the kinesin itself, that is, the effects of the internal degrees of freedom. And these fudge factors had to be fitted in, to the data. So that, in fact, say, let's put it this way, that you can measure directly a few of the rates, but this is not a complete description, even at the level of this very simplified model.
Okay, okay. Okay, thank you. So there is one more question, just.
Yeah.
Actually, I look at this. So it's not a question, but it's more a comment. So I agree with Luca that typically the chemical rates, it's hard unless you do fitting. So you have a model and you have the motion of the motor as part of time, so only the position, and you infer the chemical rates. This some authors have done. It's very challenging. Or they have some biological knowledge about the rates.
Right.
Typically, as Luca said, you have hidden information. And actually, in my lecture tomorrow, I will start discussing a very similar example. Okay. What you can do with the trajectory of the position without knowing the chemistry underlying, which is a very common situation. Thank you.
All right. Okay. Thanks. Okay, so in this case, we have the velocity as a function of the ATP concentration. Of course, let's say, so this corresponds to in some way to the imbalance, and you see that it increases with increasing concentration, and then it reaches stop. The different curves correspond to different applied forces. On the other hand, you can also fix the concentration and look at the velocity as a function of the applied force, and so this is kind of plot that you have here. We have, so the applied force is negative, and if you reduce the absolute value of the applied force, the speed increases, and these two things correspond to different values of the ATP concentration. Now, the model that we have considered has this phase diagram. On the x-axis is the applied force. On the y-axis is the imbalance of the ATP. And the regime in which you would like it to work is this A regime that is bounded by this line here. You see, it's a line goes from here to here, and goes slightly on the right of the vertical in this region here is a line where the speed goes to 0. And there is another line that is this one here, where this R is the average number of ATP molecules that are degraded per unit time. And we have this region. So in this region, we have mode A, ATP is consumed and work is performed. And let's say that the motor moves to the right. And this is the usual regime in which we would like it to work. But on the other hand, we can be in this region here. You see, in this region, R is negative. That means that, in fact, ATP is produced. You are doing some chemical work, and that the velocity is negative too. That means that you are say, moving in the direction of the force. If you're moving in the direction of the force, there is work that is done, and this work is partially converted into chemical work by producing ATP molecules. So these are nice regimes. And then there are some strange regimes here. So in this region D, work is consumed to produce ADP. So we are in a situation in which delta mu is less than 0. That means that the ATP is favored with respect to ADP, and here work is used to produce ADP. And finally, in this very narrow region C, we have that ADP is consumed to produce work. That is, strangely, you say you produce ATP and you also produce work, but this is due to the fact that the delta mu is less than 0. These other regions, white regions, are dots, where they do nothing interesting, well, nothing useful. Now, just to close the thing is, why did we introduce this complex model? Just to show you how the uncertainty relation that we have looked at work out. So in this case, we have the applied force on the x-axis, and on the y-axis we have one is the bound, that is S dot divided by KB, and these y are the corresponding quantities that are bound either for the single current, the N current, the displacement current, or the ATP production current for the model, and there is one which is related to the correlation between the R and the N currents. And what we see is that, okay, there are different values of these quantities that are bound. Let's see, this for the R current is lowest values. Then we have for the displacement current is slightly above, and then for the correlation current, let's put it this way, it is even larger. So that the fact of considering the correlations is in fact important, because it gives you a tighter connection. And I think that this is the time to stop for 5 minutes.
Okay.
Because then we go to a different subject.
Yeah. Thank you, Luca. So we can again come back in 5 minutes from now.
All right.
Okay. Thanks.
Ah.
So we can start in a minute, Luca?
All right. All
Okay.
right.
Okay. Yeah, maybe. Okay, Luca, if you're ready to start, we can.
All right. So we are going to discuss a different subject, that is the fluctuations of the first passage time. So, so far we have considered a setup in which we fix the observation time, and then we measure the integrated current, so the number of steps, for instance, of our molecule, and we have obtained uncertainty relations, which is more or less of this form, that is relation between the variance of the integrated current divided by the square mean value, times the total entropy produced during the observation time. This quantity must be larger than 2 kb, say. But there is a different way of looking at it. You fix a certain value of the current, and you ask, what is the minimal value of T such that the integrated current is equal to this threshold value? And now what we want to have is a relation on this first passage time. And what we are going to see is that the first passage time itself satisfies in uncertainty relation of this kind. That is, that the ratio of the variance of the first passage time divided by its average value times the entropy production rate must be larger than 2 kb. So to have a look of what we are doing is in this way. So on the one, here we have a diagram. On the x-axis is just time, and the integrated current J is on the y-axis. In the setup we had before, we fixed the time, and then we looked at this distribution here, the distribution of the value of the current at the observation time. And now we are doing it in this way. We are looking at, so we set this threshold value of the current, and we look at this distribution here. That is the distribution of the first passage time. So the first time in which the trajectory crosses this threshold level. So let's say that for the current, we have a large deviation expression, in the sense that the probability that the integrated current has a certain value for a certain value of the observation time can be written, say, exponential behaves asymptotically like the exponential of something that is of the form e to the minus observation times some function of the ratio of the integrated current divided by the observation time, which we can make call the mean current, if you like. It's a fluctuating quantity because for different trajectories, it will have different values. And out of this, so this is usually expressed in the by saying that the integrated current satisfies a large deviation principle. If that is the case, it is possible to define this quantity psi of lambda for a given parameter lambda. It looks like the, so you see that what you take is, you take the average value of e to the minus lambda j. That looks like, so e to the minus lambda j looks like a Boltzmann factor. And so this average value of e to the minus lambda j looks like a partition function. And taking the log, you're doing something that looks like a free energy. It's a minus a free energy, if you like. And this, since J is extensive, the free energy itself is extensive. It's like in ordinary statistical mechanics. Divided by the observation time, you get an intensive quantity that depends on this parameter lambda. And it is easy, say, you can evaluate this average by the saddle point method. So in the saddle point method, what you have here, you see, you have a lambda j. So there will be a lambda times the integrated current, and then you have minus t times this omega, which is a function of the mean current. So you write that the lambda times integrated current is given by lambda times the observation time times the mean current, which I denote here by small j. And in the limit of very large observation time, by the saddle point integration, you're looking at the minimum of lambda j plus omega j. And so you have the expression of this psi lambda that is defined in this way will be given by the Legendre transform of the large deviation function omega that is defined up here. So this is to define this psi of lambda that is a sort of a generating functional, let's say, it's called the cumulant generating functional for the current. And we define it we divide it into two branches according to the value of the derivative. Now, since the you can get by taking the derivative of this lambda, you can see, because it is a Legendre transform. So taking the derivative of this lambda, what you have is that is equal to the current itself, the average value of the mean curve. So what you have is that you can divide the lambda in two branches according to the average value of the current, whether it is positive or is negative. So we have psi plus or psi minus. Psi plus if the current is positive, psi minus if it is negative. And again, you do the same job for the first passage time. So you'll distinguish the case in which the threshold is positive and threshold is negative. For the first passage time, you assume, and in fact it turns out to be correct, that you have a larger deviation function, and the larger deviation function is now split into two branches according to whether the threshold is positive or negative. And you define in a similar way the cumulant generating function for the first passage time. put it this way: instead of the time of observation, we have the threshold, the value of the threshold, and here we have the logarithm of the exponential minus mu, our parameter, times the first passage time. So now the idea is that we are able to express this cumulant generation function in terms of the first passage time, in terms of the cumulant generating function for the current. And actually we can go by seeing that the large deviation function for the first passage time, we have to define an intensive form of the first passage time. The idea is that so the intensive first passage time is given by the first passage time itself divided by the absolute value of the threshold. And we expect this quantity to be well defined if we we look at what happens if the threshold grows and we keep this quantity finite. Then we can derive this important relation between the large deviation function of the current and those of the first passage time. So we have that the large deviation function for first passage time is given by this intensive t times the large deviation function of the current. And out of this, you get that there is a similar relation for the cumulant generating functions. And this is even simpler. That tells you that the cumulant generating function for the first passage time is equal to 1 over the cumulant generating function of the current, evaluated with the same value of the parameter. And now we're going to say just a heuristic argument to obtain this relation. So the heuristic argument goes as follows. For large values of J, so large values of the threshold, then the first passage time is simply given by the condition that the current is equal to the threshold. Because the first passage time is presumably large, and then it is true that in general the current will go up and down for a while around the threshold value, but these excursions will be very short in time with respect to the time itself, first passage time itself. So it is easy, instead of looking at first passage time, just looking at passage time by this condition. Now, if the value J is large, then we can use the probability, say that the first set, let's look at what is the probability of first passage time for this large value of J. This is given by definition, probability of the trajectory times integral over all trajectories, the probability of the trajectory times this condition, the delta that imposes this condition that we are just evaluating. But now we can use the fact that summing over all trajectories that have a given value of J, we can write this in this way. So it will be integral over all J of the probability of observing that value of J, that by the large deviation principle that is satisfied by the current can be written in this form. And having written this in this form, we can trivially integrate, because so we just substitute to t, we substitute small t times J, and so what we get is this relation. And this relation, by taking the log, is simply equal to this one. So this is very simple and very fundamental. And again, by using saddle point integration, so we have a saddle point integration, and what we have is that you just get these relations, basically. I'm not going to do that. And so we want to, oh, sorry, I got completely wrong. Sorry. I remember. So this is not the 1 over, it's the inverse. So this is, you should read that this is the inverse. I'm so sorry, got confused. So you can prove that, for instance, G plus evaluated psi plus of lambda by saddle point by the Legendre transformation is equal to minus. So this is just the definition of the Legendre transformation of omega, and this is the generating function for the time, first passage time. Now we use the expression of the generating function of the first passage time that we have here, that we had obtained before, to write this in this way. And here we have this term goes here, and you find that these two terms cancel out. And therefore we are left that the value of G plus evaluated at the value of the generating function for the current with the parameter lambda is simply equal to lambda. And that is the condition that corresponds to this formula if it had been correctly written. I'm terribly sorry. But this is easier to see in geometric terms in this way. So what we start with, this, here we are writing as a function of the intensive, of the mean current. This is a mean current. We are writing, yes, please.
Sorry, can you just quickly remind me what was lambda? I remember mu, which you got from the currents, but lambda, I think I missed.
Well, lambda is the parameter in the cumulant generating function for the current. So lambda is here, is defined in here. Well, where is it? Here.
Okay. Yeah.
Okay. And then you have the analog is mu for the first passage time.
Yeah. Thank you.
Okay, so now so here we have we write this curve here is the large deviation function for the mean current, and this is has a minimum equal to 0 for the average value of the mean current, and then of course it has one branch here and another branch here, and here with the 0 is at this point. So this blue line correspond to values of negative values of the current, and these red lines correspond to positive values of the current. Now, we go from this large deviation function to the cumulant generation function by Legendre transformation. And so this here we have as a function of the parameter lambda, the Legendre transformation that is a cumulant generating function. And again, we are considering, so this red line, so what we see here, the current is negative and here current is positive. That means that the point in which the two branches meet corresponds to the point in which the derivative, so since the derivative of the cumulant generating function is equal to minus the current. So here we have this branch in which the derivative is negative correspond to positive current, and this branch where it is positive correspond to negative current, and the minimum is obtains for the for the vanishing current. And of course, we go back to the general, to the larger deviation function by a Legendre transformation again. In this case, a Legendre transformation is an involution. Now we go from this large deviation function for the current to the large deviation function for the first passage time by the relation that we have seen before. I'm sorry here that the notation for the large deviation function for the current is I instead of being omega, but here you just read I omega when you see I. So you go from here to here by this transformation that is defined separately for the two branches. So here we have for the positive branch, and here we have it for the negative branch. And this, so here we have the, say, the intensive first passage time, the small t. And in this, this here we have the phi. By Legendre transformation, we can define the corresponding cumulant generating function. And so the cumulant generating function shown here is a function of the parameter mu. And again, we have a lower branch that corresponds to the case of positive current, and the upper branch corresponds to the negative currents. And so so what we have is that these two curves, and you see why we had to split the branch here, because otherwise we would have had a function with multiple values. But we can also go directly from this expression of the cumulant generating function to this expression by inverting. So the idea is that this curve here, this curve here is actually the inverse of this curve here. And you can get it by interchanging the x and the y axis. So you see that this curve corresponds to this curve by interchanging the x and the y axis. And this probably, so this is a very remarkable result by Gingrich and Horowitz. So I think that I said what I had prepared, and so we have a number of results that involve fluctuation, dissipation, and speed that are largely independent of system details, and they can use to infer the dissipation out of observable quantities. And in order to analyze them, it is essential to maintain thermodynamic consistency. But before leaving you, I would like to show you a photo from my family archive. I think you recognize the place. So this is a photo that was taken by my great-grandfather in Elefanta in, I think, late 1870s or early 1880s. So this is my great-grandfather, Federico Peliti, who later lived between Kolkata and Shimla. And this is my great-grandmother. And this guy here is called Luigi Firpo. He's a cousin of my great-grandfather. And he opened a restaurant in Bombay that, as far as I know, remained, existed until the outbreak of World War II. So there are some, say, far connections between my family and India that we are like to remember. And so with that, I think I can finish. Thank you.
Thank you, Professor Peliti. We will take a few questions first.
Professor Peliti, thanks for this wonderful talk. So I had one question, which is about this first passage, uncertainty relation that you showed. So I was wondering that in the initial part, you showed a proof for this uncertainty relation for currents, for integrated currents.
Right.
Does this uncertainty relation for the first passage follows immediately from this integrated current? Is that the message? So if you go back
yeah. Basically, so the only thing is that you have to use this. So basically, this is the uncertainty relations follow once you make this mapping.
I see.
Once you have made this mapping, then there is a mapping of the uncertainty relation itself between J and T.
And this mapping, does it heavily relies on the fact that large J condition, or is it valid for any arbitrary sort of?
No, well, the problem is that even in, say, I really don't think that it is easy to extend this kind of relations to smaller values of the threshold, to put it this way, because this is made simple by this fact that the condition on the first passage is only given by the value that the fact that let's put it again in this way. If you have looking at values of the threshold that are smaller, then this condition is insufficient to determine the first passage time. And therefore, we are not able simply to write this in this way. I don't know if it has been done for for smaller thresholds, say. On the other hand, it is true that for the case of currents, much is known also for finite intervals. And I'm not terribly competent on that.
And another question I have about this thermodynamic uncertainty relation, the initial proof that you did was for Markovian dynamics.
Yeah.
What is the status right now for the cases where system is doing beyond Markovian, let's say system doing non-Markovian dynamics? Is this bound?
Well, I think that this whole setup really requires Markovian dynamics. And so if the dynamics is non-Markovian, the only thing you can do is add some variables, say short memory variables to make it Markovian. I don't think there is any approach that goes beyond that. So basically that's it. As far as I know, there has been no attempts to generalize that to, say, a real non-Markovian case. It's true that something has been done, but of which now I don't remember even the reference, for a certain kind of finite, how to say, in which you're looking back at the finite time ago. So, but now I would not be able to retrieve it.
That's all right.
Yeah, but something has been done, in fact.
I have another question. So, kind of a general question. So, when I think of these uncertainty relationships in terms of the first passage times, so experimentally, this is something which is easily achievable, I guess, like inside cells, like experimentalists can measure first passage distribution. So, can you comment on whether like this kind of uncertainty relationship has been used to get some insight on like the energetics aspect of these thermodynamic quantities? So
Well, I don't know recently the details about that. Something had been done in the by 4 or 5 years ago, but it's again it was mostly on what I called analog computation, say just building up an experiment in order to look at that. I think that most of the relevance of the thermodynamic uncertainty relations is the fact that it can be used to infer quantities like, again, the efficiency that I showed you before, or the entropy production in the actual system. And from this point of view, even for having a statistics of first passage times, which is relating in fact to the time needed for a chemical reaction to take place, if it requires a number of steps, it becomes relevant. But now I would be at a loss to give you well-defined references to that.
Okay, thank you. Okay, so if there are no further questions, thank you again. Thank you very much, Professor Peliti.
Okay, thank you.
We really miss having you here in the school, and we hope in the future at some point you can make a trip to Bombay. We'll always welcome you here at IIT Bombay. But thank you for taking the time to deliver these fascinating set of lectures.
Okay, thank you for you. Did you like the photo?
It was fantastic. Yeah, I mean, the place looks a little bit different now, right?
Yeah,
So it was elephant. But the structure is still there, I think. I mean, it takes like.
The restaurant is still there, huh? Firpo.
Yeah. So actually, if you had come here, it is like a short boat journey to this